Alright, in this video we're going to take a look at a review for the solubility unit test and or for the solubility portion of your final exam. We're going to look at a handful of questions from the yellow supplementary problem booklet. So question number 17 we'll start with, and you'll notice I've made a small change in the question. It says, what mass of lead iodide, PbI2, do we need to make 5.00 liters of a saturated solution at 25 degrees Celsius? And then it tells us that the KSP is 7.9 times 10 to the minus 9 at that temperature. Now if you know what you're doing, then pause the video and go ahead and try that problem. For me, the plan that I'm foreseeing to find the mass of solid needed to make the saturated solution, I'm going to first find the molar solubility of lead iodide. Once I know its solubility, then I'll use some unit multipliers with the volume and molar mass to find the answer to the question, how many grams do I need to make this saturated solution? So first of all, let's jump in and find the molar solubility. Question 17. The salt was lead iodide, so PbI2. And when you see a KSP problem, when you see a solubility problem, you know that most of the time we write a balanced equation like this, with the salt simply dissociating into its two ions. So in this case, Pb2 plus and I minus. But because it was PbI2 over here, we need to write two I minuses over here on the right. The ions are dissolved in water, so they're aqueous, and the solid salt was on the left-hand side of that equation. We're going to set up a little ice table underneath, as we do in most equilibrium problems. Because the PbI2 is a solid, we'll ignore it in the ice table. We'll ask ourselves, what are we dissolving this lead iodide in to make the saturated solution? Well, the answer to that is we're dissolving it in water. And the reason it's important to ask that is because it tells you what to do initially. If you're dissolving in water, then initially there's no lead and there's no iodide. Pure water doesn't have either one of those. As the lead iodide dissolves, though, the lead concentration will increase, and we don't know how much it increases by. So we're going to use the letter S to represent the concentration that lead increases by, but that also reminds us that this will represent the solubility of the salt as well. Since you get 1 mole of lead for every 1 mole of lead iodide that dissolves, then the concentration of the lead's concentration in moles per liter, will be the number of moles per liter of lead iodide that dissolved. So in other words, lead's concentration in the saturated solution is the solubility of the salt as well. The iodide concentration also increases, but because there's a 2 there, it'll increase by twice as much, so 2s. And at equilibrium, we have S and 2s in the saturated solution. We'll write the KSP expression, the solubility product constant, is equal to the concentration of the lead times the concentration of iodide squared. Because the lead iodide was solid, we don't include it in the equilibrium expression. The question told us the value for the KSP. It said it was 7.9 times 10 to the minus 9. And that's equal to S, concentration of lead at equilibrium, times 2S squared. Now when you square 2s, you'll get 4s squared, and then multiplied by s out front, you get 4s cubed. Now this basic layout works for two different kinds of problems. It works for when you're given the KSP like we were given here, and you're trying to find the solubility, but we could have been given the solubility, we might have known what S is, and then 4 times that cubed would give us the KSP. So sometimes we're looking for the KSP. In this question, S will then equal the KSP value divided by 4. Since it equals 4s cubed, we'll divide by 4. And then to get rid of s cubed, we'll cube root. Now cube root you can write like that, cube root. Or we can use brackets and do this. 7.9 times 10 to the minus 9 divided by 4, and a cube root is the same as to raise to the power of 1/3. So now with my calculator, let me evaluate that. So I'm going to type in I'll open a bracket, 7.9 times 10 to the power of minus 9 divided by 4, close the bracket. And now to cube root, I need to raise to the power of 1/3. But 1/3 as a decimal is 0.33333 repeating, so I'll raise to the power of 0.33333, something like that, equals. So for me, the solubility S is equal to 0.0013. We'll keep two significant digits because the KSP had two significant digits, 7.9. So 0.0013, and this is a molar solubility. So this is the number of moles per liter of lead iodide which would dissolve in water. So that's why it's called the molar solubility. Okay? Now, the question wanted to know if we had 5 liters, 5.00 liters that we wanted to make of the saturated solution, how many grams of lead iodide would we need? To answer that, we could use one of two approaches. We could use the formula C equals N over V, followed by the formula moles equals mass over molar mass. We're trying to find the mass, so this is what we're trying to find, how many grams of lead iodide. So to do that, we would need to know the molar mass of lead iodide, which we can get from the periodic table, and the moles of lead iodide. Well, how many moles would we need? That's why we use the first formula. We know we have 5 liters, so the volume is given, and we know the solubility is 0.0013 moles per liter. Well, moles per liter is a unit of molarity, which is a unit of concentration. So where we say C in the formula C equals N over V, that can be thought of as your solubility. So we know the solubility, so the moles of salt would be C times V, and then the mass would be the moles times the molar mass, and we'd be done. I personally prefer to use unit multipliers when I do these problems, so I'm going to take my 5.00 liters of solution, and I'm going to use 2 unit multipliers to get the answer. This many grams of PbI2 are needed. The first multiplier will convert my liters to moles of PbI2, and the second one will convert the moles to grams of PbI2. The first multiplier is my solubility. The second multiplier is my molar mass of PbI2. So the solubility, 0.0013 moles per liter, that was our molar solubility. And then the molar mass, just looking on a periodic table for a moment, 207.2 is lead, plus 2 times 126.9, 2 iodides, 461.0 grams per mole. So now 5 liters, 5 times 0.0013 times 461, I need 2.996 or 3.0 grams. Okay, 2 sig figs again because our solubility had 2 sig figs in it. So there's the basic question. So we needed to first find molar solubility, then use unit multipliers, or we could have used these 2 formulas to find out that we need 3.0 grams of lead iodide to make the saturated solution. Let's look at a question which is similar, but which approaches it from the other perspective. Question number 25 in your booklet, the one at the top of the page here, says that the solubility of calcium hydroxide, CaOH2, is 0.93 grams per liter at some temperature. What would be the value of the KSP at that temperature? So notice they gave us the solubility. Now it's not expressed in moles per liter, it's expressed in grams per liter, so that's a small problem. But then they've basically given us the solubility and they want to know what the KSP would be. So we're going to approach it in a very similar way, but the first thing I'm going to do is take that solubility that they gave us and convert it from grams per liter to moles per liter. We need to have the solubility as a molar solubility. So we have 0.93 grams of calcium hydroxide per 1 liter. That's our solubility. So let's convert that to moles per liter. So we'll just get rid of the grams, then we'll switch to moles. So grams and moles is again molar mass. 1 mole of calcium hydroxide, using a periodic table, we'll find the molar mass. We have 1 calcium, so 40.08. We have 2 oxygens, 2 times 16. And we have 2 hydrogens, so 2 times 1.01. 74.10 grams is the mass of 1 mole. So multiplying like that, the grams will cancel, and we're left with moles per liter of calcium hydroxide. So 0.93 divided by 74.1, we get a molar solubility with 2 sig figs of 0.013 moles per liter. There's our solubility. Now let's go and find the KSP, and we'll do it in a very similar way. So we'll start with the balanced equation. Calcium hydroxide dissociates to calcium 2 plus and 2 hydroxide ions. This is solid. There is no calcium in pure water. Now we know that pure water does have some hydroxide. It has 1 times 10 to the minus 7 molarity hydroxide. That number is so small that we almost always ignore it, and so we will ignore it here, noticing that our solubility is actually very large compared to that. And now we could, if we wanted, do exactly what we did before. We could say plus S and plus 2S, S and 2S, and then we could say the KSP is equal to the concentration of the calcium times the concentration of the hydroxide squared. So it equals S times 2S squared. Therefore, just like before, it equals 4 times S cubed. So now finally, since we know that S is 0.013 moles per liter, we can just put that in. The KSP is equal to 4 times 0.013 cubed. And so grabbing the calculator, 4 times 0.013 to the power of 3 is 8.8 times 10 to the minus 6. There's the value for my KSP. Okay. Now there was another way you could have approached this. Let me just grab a pen here with a slightly different color. We knew that the solubility was 0.013, so that solubility would have to equal the concentration of calcium, because the calcium, as we know, is a 1-to-1 ratio with the calcium hydroxide. So someone may have chosen, instead of putting an S in the ice table here, they may have said, well, we know the solubility is 0.013, so why don't we say it equals 0.013? And then this would have gained 0.013. This would have gained 2 times 0.013, and you would have had 0.026 molarity here. Now that you know those two numbers, you could have just put those numbers into the KSP expression and found KSP that way. Personally, I prefer to do it the way we did first, with the solubility letter S and then substituting at the end. That way the basic setup of doing the problem is the same when we are given the KSP, like we were back in number 17. We can set it up in exactly the same way to find the solubility. Or in number 25, where we take the solubility, set up the same way to go find the KSP. Alright, let's look at one more problem. This is a very standard question next. It's a question of will a precipitate form? when we mix two solutions. This is question number 40, and it says, will a precipitate form if you mix 25.0 milliliters of a very dilute 0.0040 molar solution of sodium fluoride with 75.0 milliliters of 0.0160 molar magnesium nitrate. And then as a clue, it tells us the KSP of magnesium fluoride, and we can see it's very small. So will a precipitate form? Since the magnesium fluoride's KSP is so small, really we're wondering, will magnesium fluoride precipitate? So because magnesium fluoride is the thing that will precipitate possibly, what we're going to do first, this is basically a three-step question. What we're going to do first is find the concentration of the magnesium ion and of the fluoride ion, since magnesium fluoride is the thing that may precipitate. And to do that, we realized that by mixing the two solutions, we were actually doing a dilution. When you mix two solutions, C1V1 has to equal C2V2. The moles before must equal the moles after when you dilute. So the concentration after we mix, which is C2, would equal C1V1 divided by V2. And that's true for both ions. Looking back at the question, we were told that the volume of NaF, the volume of fluoride, that's where the fluoride comes from, was 25 milliliters. So that's its V1. And this is its C1, 0.004. Notice that there's one fluoride in sodium fluoride. So if you have 0.004 molar sodium fluoride, you have 0.004 molar fluoride. So we know its initial volume, we know its initial concentration. The V2, the final volume, is the total volume after mixing. So 25 plus 75, it'll be 100. Similarly, when we look at the magnesium ions, we notice that there's one magnesium in the formula for magnesium nitrate. Therefore, when we say that there's a 0.016 molar solution of magnesium nitrate, there has to be 0.016 molar magnesium ions as well. So that'll be the initial concentration of magnesium, 75 mils the initial volume, and the total volume again is 100. So putting these numbers in, the magnesium's initial concentration was 0.016 molarity. We were using 75 milliliters of that, and the total volume was 100 milliliters at the end. Similarly for fluoride, its initial concentration was 0.0040 molarity. We were using 25 milliliters of that solution, and its total volume is still 100 milliliters at the end. So the magnesium concentration after we've mixed them is 0.016 times 75 over 100. So it's going to be 3/4 of what it used to be, 0.012 molarity. Similarly, the fluoride concentration is going to be 1/4. 25 over 100 is 1/4 of what it used to be. So 0.004 times 25 over 100 is 0.001 molarity. Okay? So there's the concentration of magnesium and of fluoride. Now, will a precipitate form when we mix these solutions? To decide that, we're going to calculate the value of QSP. The salt's formula is MgF2, so QSP, which is the reaction quotient, is equal to the concentration of the magnesium ions times the concentration of fluoride squared. And we know that this expression is based on this reaction, right? Mg2 plus and 2 fluorides. And we remember from our equilibrium unit that if a value of the reaction quotient, Q, or in this case QSP, if it's bigger than the equilibrium constant for the reaction, so if Q is bigger than K, we know that the reaction shifts backwards. That's because the equilibrium is trying to reduce the value of Q. It's too big, and to do that, it's going to shift backwards to lower the concentrations of those ions. Notice that in shifting backwards, we'd be forming solid. solid magnesium fluoride. So we would see a precipitate, PPTE, precipitate, if the reaction shifts backwards. And the reaction would shift backwards if QSP is bigger than KSP. So we're going to calculate QSP, and that's why we needed these two concentrations. So magnesium 0.012 molarity, and the fluoride 0.0010 molarity squared. Okay? And so grabbing a calculator, 0.012 times 0.001 squared is 1.2 times 10 to the minus 8. There's the value of QSP. Now the question told us that the KSP for magnesium fluoride is 6.4 times 10 to the minus 9. Therefore, our QSP is bigger than KSP, and therefore the precipitate will form. If the QSP were equal to the KSP, then the solution would have been perfectly saturated. It would have been at equilibrium, and there would have not been a precipitate. If QSP were less than KSP, then the solution would be unsaturated. More ions could have been present, and then again there would not have been a precipitate. So you only see the precipitate if the equilibrium shifts backwards, and that would be when Q is larger than K. So the basic steps in this problem are 3 of them. The first step was to find the concentrations of the 2 ions that might precipitate, and we knew they were magnesium and fluoride because the question told us the KSP of magnesium fluoride. We found those concentrations after diluting because we were mixing 2 solutions so that we could plug them into the QSP expression. Calculating QSP, our second step, that led us to the third and final step, which is simply to compare the QSP to the KSP. And we found that it was larger, therefore the precipitate does form. So those are 3 standard questions for solubility equilibrium. They're not by any means all that you need to know for this unit, but they do form, if you really understand those well, then they form the heart of this unit. You should do relatively well on the unit if you understand these. Be sure that you're also using your data booklet's checklist for the unit. In it, this is at the beginning of your data booklet, it's also on your Edmodo page. There are a list of things that you need to know for solubility equilibrium. And I think you'll agree once you look them over that we have done all of those problems in class. So good luck in preparing.